Once we know how to convert a system of equations into an augmented matrix, the next thing to do is to look at understanding the three basic row operations that we can apply to manipulate and work with matrices. The first is that we can interchange two rows. So looking at our first augmented matrix that we have written here, we could look at taking row 1 and repositioning it as row 2. So that means all of our values in row 1 will get shifted down to row 2, and all of the values in row 2 will take their place in row 1. So this augmented matrix would be rewritten as 6, -5, 6, 4. Row 2 would become 1, -4, 4, and then 2. And our third row would remain unchanged. So none of the actual numerical values have changed with this row operation. We just switch the places or the positions of two rows. The second row operation that we can perform would be to multiply any row by a non-zero factor. That would mean we could take any row and multiply it by any number we want, as long as that number that we're multiplying, isn't 0. So in this case, what we'll do is look at updating row 1. And the way we'll update it is by taking 3 times all of our values in row 1. With this notation just indicating sort of what I said, the row that we're updating, and then the way in which we're updating it. So using capital R to reference which row we're updating, and then lowercase r's to indicate how we're making those changes. So what would happen in this case would be that every single value in row 1 would get multiplied by 3. So row 1 would become 3, -12, 12, and then 6. And then our other two rows would be completely unchanged by that row operation. Our third row operation is the most complicated one, but it's really only a couple of arithmetic steps. So what we'll do is replace a row by the sum of itself and a non-zero multiple of another row. So that one sounds much more complicated than the others. But what we'd be looking at doing would be something like updating row 1 by taking all of the values in row 2 times 2, and then adding that result to row 1. So keep in mind, when we make this row operation, the only thing that's being updated is row 1. So row 2 and row 3 are completely unchanged. But what will happen is row 1 will get updated. We'll be taking 2 times whatever our value is in row 2, and then adding that to row 1. So to start off, we would take 2 times 6, which would be 12, and add our value in row 1 to get 13. Then we would take 2 times -5, which would give us -10, and add -4, which would give us -14. We would take 2 times 6, which would give us 12, plus 4, which would give us +16. And then we would take 2 times 4, which would be 8, and add 2 to get 10. So we updated a row by multiplying all of the values in row 2 by some non-zero multiple, so anything besides 0, and adding each of those results to the value that we already had in row 1. These row operations start to make more sense as we work with them and actually move towards our goal, which is going to be to rewrite each of our augmented matrices in what's referred to as row echelon form. Or in the language that I like to use, we want to rewrite each matrix as an upper triangular matrix. And we'll see in a minute why we can refer to it as an upper triangular matrix. So given this augmented matrix, which represents a system of 3 equations, what we would want to do is manipulate our matrix until our first row, first column, starts off with a 1, and all values below that are 0. Second row, second column should be a 1, and all values below that should be a 0. And then third row, third column should be a 1. And then all of our remaining values can be any number. There's no specific restriction on them. They'll just be the numbers that they turn out to be as we perform those different row operations. But what we end up with then is this diagonal of 1s, which gives the left-hand side of our matrix, so everything to the left of that vertical bar, sort of this upper triangular pattern, where we have a row of 1s along the diagonal, some values up above, doesn't matter what those turn out to be specifically, and then everything below that triangle represented as a 0. We would want exactly the same thing if we had a larger system. In this case, we have a system of 5 equations. We would still want row 1, column 1 to be a 0. And then everything below that, row 1, column 1 to be a 1, and everything below that to be a 0. Row 2, column 2 would be a 1, and everything below that would be a 0, and that pattern would continue to repeat. Until we have that upper triangular form on the left-hand side of this vertical line. If we have additional rows, those rows would just go to 0. And then again, we would have whatever remaining values that we would end up with, which would be determined by those row operations. But regardless of the size of our matrix, what we would look for is something in row echelon form, or again, something that has that upper triangular nature on the left-hand side of that vertical bar.